Hello, good morning. Okay, so welcome. Right, so as I said, the announcement, basically two more lecture material left. Right, one is this week, okay, on the memory. All right, and next week is also on memory, but that is on virtual memory. Okay, so we just have two more lectures. All right, so they are both fairly short lectures, so I think we should be done within the hour. All right. Yeah, so we still have a tutorial this week and next week, okay, to cover this material. All right, and this Friday is your project assessment, so please make sure you have gone through the assessment document that I uploaded, right, to understand all the things that will be assessed and the timing that I mentioned as well. Okay, yeah, so I think let's get started. Okay, so yeah, so today's topic is on memory. Okay, so for us to get a better understanding of how we use the memory in our system whenever we write our code and compile it, and also when it is running in real time. Okay, so these are all the things we'll be covering. Okay, so let's just go straight into it. Okay, so in terms of memory, all right, the thing that we are always more familiar with is the code that we write. All right, so when we open up our editor, we write our code, okay, and eventually we compile it. All right, so that code that we write, okay, where does it go? Okay, it goes into this part of the memory known as the text segment. So this is known upfront. All right, so the OS knows in advance because when you compile the code, it already tells you how much of memory space it occupies. Okay, so that goes into the part of the memory known as the text segment. At the same time, we declare variables as well, correct, in our code. All right. So in terms of variables, okay, there can be different types. Okay, so one of them are what we call the global variables and static local variables. Okay, so for global variables and static local variables, we have two possible places where the compiler might place them. If they are initialized with a value, all right, then they go into this data segment. Okay, if you declare but you do not initialize, then they go into another segment called the BSS. Okay, where it is initialized to 0 by the compiler. Okay, so when you declare any global variables or static local variables, then we can place them in either the data segment or the BSS segment of your memory. Then we also have runtime allocation. Okay, so in runtime allocation basically means the system does not know in advance, correct? For example, you are getting some incoming data, correct? And you do not know how much data. Okay, so you need to process the data after you receive it. Okay, so how much memory you need to process the data, you only know after you have received that whole chunk of data that has arrived. Okay, so in that case, what you can do is you can use what we call a malloc. Okay, so in malloc, basically what happens is you do runtime allocation, and after you have finished using the memory, you should call the free to deallocate the memory. So this is stored in this segment called the heap. Okay, in the memory layout. And the last one is what we call the stack. So stack is used for a few things. So one of the common things is for function parameters and local variables. Okay, so if I have a main function, okay, and I call a function f1, okay, and I pass parameters. Okay, so when I go into f1, okay, I need to be able to retrieve these parameters. So this will be pushed onto the stack. Okay, which will then be retrieved in the actual function. Okay, and the other thing is, of course, your return. Okay, so when I finish the function f1, I need to come back to this line. All right, so that return address is also on the stack, the return address. Okay, so you also use the stack for the local parameters. Okay, that means local variables. So within the function f1, when I declare variables, integer x, y, and so on, those are also on the stack. All right, so stack is very commonly used. Okay, if you go at the assembly language level, stack is operated using the push and pop. Okay, so you can push and pop onto the stack to access the variables. Okay, that have been stored there. So this is the general sort of layout summary. Okay, so you have text segment, data segment, BSS, heap, and the stack. Okay, so let's again, this is an example of the stack that I mentioned just now. So you have a main function. So when I run this code, when I first load the main, I already have 3 local variables, A, B, and C. So they will occupy the stack space. Then when I call function f, I will also have to set aside the space for x and y. So A and B will be passed to x and y. So A and B will be pushed onto the stack, which will be retrieved by x and y. And then the temp is also another local variable within the f function. So temp is also on the stack. Okay. So of course, what is not shown here is the return address. So I also need to store the return address over here. Okay. That means where do I go back to after I finish the f function? Okay. So this is an example of how the stack will grow as you call functions and you return. So when you return from f, those variables that were originally in the f function is considered pop from the stack. Okay, so this idea of pop from the stack, okay, doesn't mean that the data disappears. It doesn't mean data disappears. Okay, so when you say you pop from the stack, basically mean that your stack pointer. So if you remember your assembly language, basically you have a stack pointer that will keep on adjusting depending on whenever you push and you pop and so on. Okay, so if my stack pointer is pointing here and I say I pop 3 variables off, so my stack pointer goes back here. Those 3 variables or those 3 data segments are still there. Okay, so I can still manually adjust my stack pointer to point back to the same address and retrieve the data. Okay, so it is still there, but it's just that we consider it as pop because it is no longer considered as data that is expected to be there, which means it can be overwritten anytime. Okay, the next time something else goes onto the stack. Okay. Now let's look at an example here. All right, so this example gives us an idea of how all of this, or this code segment might occupy some memory space. So if you look at this function, okay, so the first thing you notice is this entire function that you write, that is a code. All right, so all of that will go onto the text segment of your memory space. Then you have one global variable and one local static variable, which are both initialized. Okay, so as long as they are initialized with some value, they go into the data segment. Then you also have another variable, which is a global variable, but it's uninitialized, so that goes into the BSS segment. Okay, and then you have your malloc over here. So this is for runtime allocation. So while the program is running, depending on the value in high size, you will allocate some memory. Okay, and when you allocate a memory, you get back a pointer to the address. Okay, so P is pointing to the address that has been set aside by this malloc operation. Okay, and then subsequently, what happens? Okay, so what is next? Your character P. So this is actually a local variable. Okay, it's created within the f function, so it's on the stack. Okay, so it's on the stack of the function f over here. Okay, so you can sort of see that in this one example, you are basically occupying all the different regions of the memory. Okay, in this variables and this function over here. So what are we? When is memory allocated and deallocated? So for global and static variables, all right, you are allocated at program startup. Okay, because the moment you start a program, you already know that you have some global variables and static variables, so they are already allocated at the data and BSS segments. For local variables, it is a function call. That means when I call the function, then those variables are sort of loaded onto the stack. and then I clear it when I return from the function. Okay, similarly for dynamic memory is when you do malloc. Okay, so the thing we're going to look at next is some of the issues with some of this memory allocation, and how some of the policies that the OS may use to allocate and deallocate to manage the memory that it has. Okay, so let's look at this idea of the dynamic memory. So as you know, the dynamic memory is the space set aside is what we call the heap. That means in runtime, whenever I want some memory, I need to request for memory from the heap. Okay, so in this example, first I do a malloc of 3. That means for now, you just take it as maybe 3 bytes or 3 chunks of memory. Okay, then again another malloc 1 and then malloc 4. Then once I'm done with using P2, then I free it. Okay, and then I allocate P4. Okay, another malloc of 6 units. Then I free P3. So the memory allocated for P3 is now freed up. And then I allocate again malloc 2 pointing to P5. Okay, so you can see that every time I malloc and I free, I start to see what we call fragmentation. Okay, that means the whole memory parts of it are used, parts of it are free, and so on. Okay, so these are things that we need to handle it correctly. All right, if not, what will happen is you have a lot of these broken chunks of memory regions, and it may become a bit more challenging to allocate later on in the future. Okay, so what are some of the common issues, okay, with dealing with memory allocation? So if you look at this example, what is happening here? You call a function f, okay, you do a malloc, all right, and then you return, and you continue with the rest of the program here. So whenever you call f, what happens? You jump into f function, you allocate some memory, and then you return. Now this kind of system, what will happen? When you run very nicely today, you will run nicely tomorrow. Then every few days, the whole system will crash. Okay, the whole system will crash, and then you can't figure out what happened. All right. So why does it crash? Because over here, okay, we allocate, but we never call the free. Okay, that means we never deallocate the memory. All right. So what happens? So every time I call f, it allocates some memory, But at some point of time, you don't have any more memory, correct? Because everything is taken up because you don't free it. And then the whole system goes haywire. Okay, and then the crash happens. Okay, so these are small things, but can lead to very, I would say, stressful bugs to catch. Okay, why is very stressful? Because these are things that may not show up at all. Firstly, it's not a compile error. Okay, compiler will never catch this as an error, and in some compilers they may flag as a warning. Okay, but again, depends on how smart the compiler is. Okay, so it may be difficult for you to catch that this is actually the issue. All right, because you don't see any warning, you don't see any error. Okay, so these are things that you need to be aware of. Okay, when you're dealing with memory allocation or dynamic memory allocation in your code. Okay, if you're just everything is static, then it's fine. Yeah, but as long as you're doing dynamic allocation, you need to be very careful that you free up the memory after you use it. Okay, another common mistake, okay, that programmers will make is this. Okay, where you have a variable, you have a function, and you create a local variable. So when you create a local variable, it's on the stack. Okay, and what do I do here in the main? I'm calling the f, and I'm expecting a return. Okay, that is fine. But what do I return? I return p. And what is p? Okay, p is basically, okay, if you remember your C programming, p is equivalent to the address of p0 because p is an array. Okay, so this you are trying to return the address of the first element in this array. But what is the problem? The problem is this p is created on the stack. Okay, so if p is created on the stack, then the moment I return, yes, I will get a value. You will not show as error. Okay, you will still compile, it will still run. But the problem is, you cannot guarantee that the original data that was in this address location P will still be valid later on, because the stack is very dynamic. But as long as the program is running, the functions being called, there will always be usage of the stack. Okay, so at this point of time, yes, your pointer is pointing to the correct sort of value. Okay, but after that, it may get overwritten anytime. Okay, so these are again things that you must be careful about, because it's pointing to data that's not there anymore. Okay, because once you come out of the function, you consider you pop from the stack already. Okay, so that data, that address may no longer hold the data that you expect it to hold. Okay, so these are what we call dangling pointers, which again you need to be careful about. Okay, so next we're going to be looking at some of the memory allocation concepts. Okay, how do we allocate memory? How does the OS manage it? Okay, so in terms of memory allocation, the concept is very simple, right? That means whenever I call malloc, okay, I specify how much space I want. Okay, and the OS is supposed to allocate that memory for me and return me a address that points to the start of this memory chunk that I requested for. Okay, so in this case, 8192 is the address. So this is the starting address, 8192. And at this address, I have 4096 bytes, okay, of memory allocated for me. Now, when you do this kind of memory allocation, okay, the issues are what we call external fragmentation or internal fragmentation. All right, so let's understand what these two terms mean. In terms of external fragmentation, okay, basically what happens is in external fragmentation, is caused when you have dynamic or variable allocation sizes. Okay, so for example here, if I request for 4 chunks here of 100, then it will just give me the 4 blocks. Then when I free the second and I free the fourth, okay, and then I request for one more, which is 200, then there is a problem. Correct? Why? Because even though I have 250 of free space available, correct, 100 here, 150 here, okay, but it's not contiguous, correct? It's not one contiguous chunk. Okay, it is broken up. So because of that, this malloc will fail. All right, so this is what you call the external fragmentation. Okay, so I can allocate based on whatever size I want. Okay, but then because I allocate and deallocate as and when I need, okay, then there may come a point of time where I have the memory, but it's all broken up. Okay, then I can't allocate it. The other issue is what we call the internal fragmentation. This is where you have a fixed allocation size. Okay, a fixed allocation size. That means I always allocate in multiples of certain number of bytes. So in this example, we're looking at 100 bytes. Okay, so if I stick with this allocation size of 100 bytes, okay, when I ask for 90, you allocate 100, okay, but 10 is free. Okay, so I allocate the first 100, but 90 is used, but 10 is free. Okay, similarly, when I ask for 120, it has to allocate 200 bytes, but I only use 120, so 80 are free. Okay, and then when I ask for another 10, okay, you give me 100, but I only use 10, so 90 is free. All right, so this is internal fragmentation, because you see I have a lot of free space. Okay, I have a lot of free space, but when I ask for just 50, okay, it's not possible. Okay, it's not going to give me because I don't have any more free allocation units. Okay, because everything is in multiple of 100 bytes. Okay, so this is another issue, internal fragmentation. So in terms of internal and external, all right, for external fragmentation, what we can do is we can do compaction. Okay, that means we can compact the memory later. Okay, which is I think most of our laptops and computing systems have this disk defragmentation tool. Okay, which you sometimes it may be programmed to run on its own, or sometimes you can trigger it. And what it does is it does this, correct? It tries to look at the memory usage of your hard disk and tries to compact it. That means those files that are broken up all over the place, it tries to compact them together into one continuous chunk so that it is a lot more efficient after that. All right, so that is the thing that we can do. Okay, so for external fragmentation, okay, in order for us to keep track of where we are, how much we have used, what we need to do is we actually need to keep track of what we call a linked list. So a linked list is basically a series of pointers. All right, that means you have one element point to another element, and then it stores the pointer to the next element and so on. So it's a linked list. So in a linked list, what we're going to do is we're going to point to the next available free space and the previous available free space. All right, so if currently this is my starting point over here, then I will have a pointer that points to the next available free space and then the next. And at the same time, I will also have another pointer built in to point to the previous address and so on. Okay, so why do we need this? This is to help us later on when we want to figure out whether we have any free space that we want, and at the same time to do the compaction later. Okay, so whenever I free up some chunks and I want to do a compaction of memory, then these pointers will help me to know exactly where these free spaces are. Okay, so in terms of this free list, okay, what we want is we want the holes to be as large as possible. All right, why do we want the holes to be as large as possible? Because when I have a large hole, okay, it's easy for me to allocate different sizes. So I can have a small size, a big size. Okay, but if I have very small holes, then it's very difficult for me to allocate. Okay, unless it's really a limited amount of memory that I want. Okay, so for this external fragmentation, we want to manage it by having free holes that are as large as possible. Okay, so whenever you deallocate memory, what you want to do is you want to do a merge. Okay, so when we do a merge, we are going the direction of trying to make the holes as bigger as possible. Okay, so for example, here, if I have two chunks of memory that are used here and here, okay, and the first one is freed up, okay, then I can't do any merger yet, okay, because it is still two separate chunks of memory. Okay, but if I free up the memory space before, okay, that was originally occupied, okay, then I can do a merge. All right, and whenever I see a hole, I can do a merge. So in this case, this free space and this hole are considered both empty, so they can both merge together and create a bigger hole. Okay, similarly to the right, or if all three are freed up, I mean all two are freed up, then all three can merge together to create a bigger hole. Okay, so the main aim is we want to make the holes as big as possible, correct, to allow the mergers to happen. All right, because when you have bigger holes, then subsequently when you have a memory allocation request, it's easier to fulfill. All right, so how do we do this? Okay, so for example, now I have this usage of the memory, and if I free up this chunk over here, then what will I do? I can see that now I have, this is a free space, okay, and this is also now freed already. All right, so what I can do is I can now readjust my pointers, okay, and merge both of them together. So now I have a much bigger free chunk, free hole over here. Okay, in terms of allocation algorithms, okay, so the OS may employ different algorithms depending on how it is configured. So in terms of the popular ones, the best fit is one where it picks the smallest hole. Okay, so if I ask for an allocation unit of 150 bytes, for example, I will start from the beginning of my free space and I traverse the entire region for all the holes. Okay, and then I try to pick the smallest hole. Okay, that will satisfy the request. All right, so what happens is, of course, over time, you have a lot of very small holes everywhere in the memory. Okay, because it picks the smallest hole. The worst fit is it takes the biggest possible hole. Okay, so if I take the biggest possible hole, what happens is I still have a lot of free space in that hole to still satisfy more requests. Okay, until it reaches a point where you may have very or too little space that you can use it anymore. Okay, so that is the worst fit. The other one is first fit and next fit. The first fit is the moment you find the largest hole or the hole large enough to satisfy the request, you straight away take it. Okay, so for example, if I request for 150 and the very first hole that I come across is big enough to satisfy, I straight away take it. Okay, next fit is same as first fit. Okay, except that you continue from where you left off. Okay, that means if this example, if I allocate 150 here, that means I already use 150. Okay, so left over here is 850. Then I will the next. So the beginning is still here, correct? I'm still here. Okay. So let's say now I request for 1000, correct? So if the next request is 1000, this is not big enough, so I'll come here. Then I allocate 1000. Okay, and then I'll point here. Okay, so if my next request is 150 again, okay, or maybe 200. Okay, in the next fit, okay, I will always continue from where I left off. All right, whereas in the first fit, I'll go back to the first available hole and then start again. So the next allocation will always go back to the beginning and start all over again to see where the first hole that is big enough to satisfy the request. Whereas the next fit will just continue from where it left off and then wrap around to the beginning. Okay, so they are both quite similar in that sense. Okay, so these are all just allocation algorithms, all right, that may be utilized whenever you call malloc, okay, to allocate memory for the code. Okay, so just now we talked about the compaction, all right. So we have two issues, internal and external. All right, so for internal fragmentation, we have this segmentation, all right, which is part of the virtual memory, which we will cover next week. For external fragmentation, okay, we can do what we call compaction. So what is compaction? Compaction is actually to take all these chunks, okay, and free spaces and pack them together so that all the holes go to one side, one end of the memory, and all the chunks or the use spaces go to the other end of the memory. Okay, of course, when I draw like that, it looks very easy, right? But it is actually a lot more complicated. Why? Because you really need to keep track of all the pointers and you need to move data around from one space to another space correctly, okay, without overriding any existing data. Okay, so there is a significant amount of work to be done. All right, so the idea is simple, okay, but in terms of doing it, it takes a fair amount of effort and a lot of resources. Okay, so it may be a simple concept, but it's again there's a lot of overhead. All right, so of course, if you use what we call the DMA, the direct memory access of the system, you can still do this a lot more efficiently. All right, but it still requires a fair amount of memory movement around. Okay. So another way of managing requests, all right, is where you upfront create multiple lists of different hole sizes. So instead of saying that I go through the list from the beginning and then try to look for the best fit or the next fit, okay, I upfront allocate different chunks of memory, okay, or for preset sizes, okay, and then whenever I have a request, I pick one that matches it to the closest. All right, so in this example, you have a list of 64 bytes of memory, a list of 32 bytes of memory, and so on. So whenever I have a request, I immediately allocate based on the closest size that fills the requirement. Okay, so that is one way of doing it. Okay, so what you can do is you take with the largest total amount of memory you have, and then you keep dividing it by 2. okay, until you have one that matches the requirement. So if I want, for example, 3 megabyte, and currently I have 16 megabytes, so I keep dividing by 2. So I divide by 2, so I get 8 and 8. Then divide by 2, I get 4 and 4. Okay, then from there I can pick one to be allocated to this. Okay, so that is one way of doing it. All right, so in this example, if let's say I request for 100K. Okay, so let's say I request for 100K of memory, then what will happen is this 1 megabyte will have to be first split into 512 and 512. Okay, and then split again 256, 256, then 128, 128, and then I out of the one of the 128K blocks, I allocate one of it. Okay, and then you still have all these other blocks available that are free. So the next time there's another request, you can then go ahead to allocate or speed up some more. Okay, depending on what is the requirement. Okay, so the idea of this buddy system is an extension of the free list. Okay, so it applies to the free list where you merge based on who is a buddy. Alright, so when I split, what happens is I automatically create pairs. Correct. So when I create pairs, I need to make sure that the pairs are aligned to the higher level boundary. That means when I look at this level, the pairs that I take must be aligned to the higher level boundary. So the higher level boundary is this and this. So I say that this and this are a pair. Okay, so this and this are not a pair or not buddies because they cut across the higher level boundary. Okay, and why is this boundary important? So it makes sure that you always merge together to match or to keep the original free list still intact. Okay, so the original free list is you always divide by 2 from the highest to the lowest. Okay, so when you merge back, you go back in that same order. Okay, so that is the idea of the buddy system. All right, so you always break it up into pairs. All right, and then you merge based on the boundary. Okay, so let's look at an example. I think it's easier for us to relate. So I have 1 megabyte of memory here, and I say allocate 100K. So first I will speed up, correct? 512, 512. Again, it's very big, so I speed up again 256, 256, and then I split one more time. So I get 128 and 128. So out of the 128 and 128, one of it will get 100K. Okay. Now the next time I allocate 64K, I have already a 128K here, so I can split up that into 2 and then allocate 64K. Okay, so you can see that this multiple free list works by always looking for the currently smallest memory list, and then from there you decide whether to go up or go to the one level lower. So if I ask for 240K, the closest will be the 256K, and then you will allocate 240K from there. Okay, if I ask for another 256K, then what happens? Then I need to split up the 512K. Then I get a 256K. Now, if after that, if I free the 240K, what happens? I free this, but I cannot merge. Okay, this and this are not buddies. Correct? They're not buddies, so I cannot merge them. Okay, so I free up the 240 means I get 256K free, but I cannot merge them. Then when I free up the other 256K, then this and this are buddies. Okay, they are buddies, so I can do a merge. So it becomes a 512K. Okay, so you merge only based on the alignment to the higher level boundary. So that's how the buddy system actually helps to maintain the hierarchy as how it was originally created. Okay, so that sort of is all we have to cover for this topic on memory. All right, so like I said, it's a fairly short topic just to give us the idea of how memory is utilized in the system. Okay, so for the tutorial, there are also some questions, okay, that we will go through, okay, with the tutor to understand this a bit better. Okay, so again, just a reminder about the project assessment this Friday. Okay, I just want to again highlight a common question that I've been getting regarding the second challenge. Okay, I just want to highlight this. Okay, so a lot of students have been asking about this. All right, so I just want to clarify. Okay, the robot is supposed to go around. All right, so the ultrasonic sensor or whatever sensor that you use is to detect the obstacle. Okay, the obstacle is your 4 toilet rolls that are packed together. Okay, once it detects, it goes around, correct, and then it comes back. When it comes back, it has to cross this sort of a red line here. Okay, whether the line is there or not, as long as it crosses back into that the place where you started from, then it's considered valid. Okay, it's considered a valid run. That means if your robot goes around but stops halfway before reaching this line over here, then it's not considered a valid run. Okay, that means you don't have a timing. Okay, you only have a valid timing when you come back and cross this line. Okay, so that is the first thing. Now the second thing is to come back here and stop. Okay, you can use anything to stop. Okay, you don't need to use the same toilet roll or anything. You can just use your hand or anything to trigger it to stop. You cannot physically touch it, okay, but as long as you use the same sensor to stop it, that means it's fine. Okay, but what you want to place to stop it is up to you. Okay, you can place a book, you can place your hand, whatever. All right, but you cannot physically touch it, but you can use anything here to stop it. All right, and you can manually adjust this as your robot is coming back. Okay, so you don't need to have it in a fixed place over here. Okay, it doesn't mean that, okay, I put it here and it must stay there. No. Okay, you can manually adjust this, okay, as your robot is coming back. Okay, so that you can try to stop it as close as possible within the box. If you stop within the box, then you don't get any penalty for any additional penalty. But if you stop outside the box, that means any of the wheels touch outside of the box, then you consider to have some penalty marks for that. Okay, so that is one thing I want to highlight, because I think quite a few emails have been getting about this. Okay, so that sort of wraps up today's class. Does anybody have any questions you want to ask about the content or the project assessment?
Sorry, Prof.
Yeah.
Can I just verify? So this Friday we'll be submitting the robot at the start of the lab session, is it? And then waiting for our run.
I already sent the announcement, but it's at 1 hour after your lab starts.
Okay.
Okay, so if you have the morning class, you submit at 7, the afternoon class, you submit at 3.
Okay, thank you.
Okay, so anybody has any other questions you want to ask about the assessment this Friday? Okay, so I mean, morning 8 to 10 is still considered a free time. Okay, so you can still come in to use the lab, but 10 o'clock, only those who are supposed to be in the lab group are allowed to be in. Okay, but before 10, if you the afternoon group comes in, that is still fine. That is still open lab access time. Okay, but 10 o'clock onwards, only the first group can be in. Okay, for the lunchtime, I will talk to Uncle Jalil to see what time we can open up. Okay, so that the afternoon group also has some additional time to prepare. Okay, so any questions? If not, we can end for today. Now, see you all on Friday, okay, in the lab. Okay, so thank you. Good luck. I'll see you on Friday.